Okay, well, today we have uh, Doctor Who is a theme. um, so, for those of you watching at home. Um, okay, so for Chapter 3 homework, one thing I want to make sure everybody was aware of. Um, in section 3.2, will be the only problem I assigned. Number 2, part C, there's a typo. You're supposed to show that T is continuous, as defined earlier in the problem, not F. And also, another thing that is important for a problem as a whole, so all parts, the constant Q that's mentioned in the problem is less than 1. They forgot to mention that. That's what actually makes a contraction a contraction. Because otherwise, the conclusion in part A is somewhat invalid. Okay. And I swear to God that by Monday I will have the graded homework ones back to you. Although there are certain ones, more than one, it took me a long time to receive. So it's partly on you guys. And I haven't received everyone's homework 2s yet. So hopefully that'll be coming soon and I can then fall behind on those. Okay. Meanwhile, so every chapter is worth talking about because now I'm continuing on with chapter 4. So I'm going to pick up where I left off last time. Okay. And it's going to be interesting to work around this stuff. Well, it'll be pretty easy over there.
You did it the other day.
Yeah. But it makes it interesting. So I figure this is my way of contributing to the art. Actually, that's kind of reminding me of, Haley, what I showed you earlier today, that evil math costume or something like that. Yeah. So.
Exactly.
Okay.
Remember, in place of F, M, and N, well, you should replace that with T.
Whoa, what?
Like,
Yeah. Because the problem is you show F is continuous.
T is continuous, right?
Yes. Alrighty. Okay, so I'm finishing up with section 4.3, the constant coefficient linear system. I'm recording, right? Yeah, okay. That'll be bad. Okay. So the flow, I'll make a quick comment about that. Of some data x from time u to time t is e to the a t minus u times x plus integral from 0 to t e to the a t minus s b of s ds. Okay, now one thing I just want to highlight something about this formula. And by the way, I've updated the notes for this section, or these sections 4.2, 4.3, just to try to make the explanations a little clearer. So the way this flow formula works is, the e to the minus au, what it does, it takes the your argument to your flow map, your x, back to time 0. The lower limit here is u, not 0. Okay, so the negative sign here for this part is saying, okay, taking x, which is specified at some time u, and I'm going backwards all the way to time 0. And then the e to the a t that is applied here for positive exponents, then we're going back forward in time. Time t. So what's happening is, okay, so x starts here, and you're going back to here, and really, this applies not just in this constant coefficient linear case. This is actually true of systems linear systems in general. So what you get here is basically g of s inverse, or sorry, g of u inverse x to get back to time 0, and then you leap forward back to time t, and it's, so in a homogeneous case, basically it's g of t, g of u inverse. Can't write x. Okay, so this is a way to better understand how the formula for the flow map in these linear systems behaves. And the thing is, with nonlinear systems, it's a little harder to see it that way. So there's a semi-group property. You could think of it that way if you want, but this actually going back in time by step u and then forward by step t to accomplish what's really happening here, to try to see what happens to x going from here to here. This two-step process is a lot more apparent in the formulas for linear flow maps than for nonlinear ones. Okay. All right. Now, so that's one thing I want to mention about these flow maps. And the last thing I have for this example, before we move on to the dreaded section 4.4, is have an example. We want EVAT for a particular matrix. A is 1, 1, 0, 3. So how can we compute this explicitly? Now, for a small matrix like this, that's easy to take powers of, you can actually use the Taylor series definition of EVAT. So EVAT is a sum of 1 over k factorial a times t to the k. So this requires powers of a. So let's go ahead and take a look at those. Sometimes what you can do is, especially with a small upper triangular matrix like this, see a pattern after the first few powers. So if you go ahead and compute a squared, so I won't carry out all the multiplication details here. You guys know how to multiply matrices, right? Or at one time you did. Okay. This is something that Dr. Schroeder and I were talking about earlier today, just about just students in general, that it seems a lot of things just get forgotten. So.
First row times by first
You
column.
don't use it, you'll lose it.
Yes,
The
and
first
apparently
entry.
it's necessary to use it, but apparently not sufficient. Yeah, and when you do all that, this is what you get. You get 1, 9, 0, and then 4 for a squared. And then we'll look at a cubed. So that is 1, 13, 0, 27. And finally, a to the 4th is 1, 0, 40, and 81. Okay, so if you look at these numbers, we go from a to a squared to a cubed to a to the 4th. We'd like to have a pattern for a to the k. What patterns can we see in any of these numbers, besides the obvious that the lower left element is always 0? Because you multiply upper triangular matrices, you get upper triangular. But what else do we have?
1 to the k. You're adding
3
to
to
the k.
the 3 to the k.
3 to the
Yeah, you have 3 to the k on this 2, 2 element. Okay, so this is a triangular matrix, so the diagonal entries are just the eigenvalues. And when you raise a matrix to a power, the eigenvalues are raised to that power. Okay, so we have this relatively simple pattern here. What about the other one?
You're adding the second column. to
Oh,
the
okay.
entry.
So difference between 4 and 1 is 3, 13 and 4 is 9, 40 and 13 is 27.
Yeah, so what's happening is, so here you start from 1, you add 3 to get 4, 9 to get 13. So what happens is it's actually a sum of powers of 3. So the way we can write it is a sum. So for instance, in this last one, k is 4. So we have 1 plus 3 plus 9 plus 27. So we're adding powers from 0 up to k minus 1, 3 to the j. Now the thing is, to express it as a summation like that is kind of a pain. We don't want to do like a dot 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 or anything like that if we don't have to. Fortunately, we do have a formula for this in closed form. So use the fact that 1 plus r squared and so forth up to r to the n is r to the n plus 1 minus 1 over r minus 1. So if we use that here with r equal to 3, then we can condense this nicely. Make sure I'm getting this. Okay, so we have 1 to the k, 0, 3 to the k. So applying this formula here, our stopping point is k minus 1. So here we're going to have k, so 3 to the k minus 1 over 2. Yeah, so we just have that. So here's our nice explicit closed form expression right here for a to the k. So now we can take that and plug that into our power series representation of the exponential in order to get an explicit formula for e to the at. All right. So now what we have is, let's see, I'm sure.
Dr. Lambert, do we need to write 1 to the k? Because
Well, it's going to become moot in a second. So, yeah. All right. But I technically know, but because we're combining the t to the k. So e to the at is now going to be a sum. Okay, I'll make sure this is not. Yeah, what's bugging me is there's, like on this part of the board, I don't know, you may not be able to see from where you're sitting, but I'm just watching myself on
The
the,
glare.
yeah.
Yeah, there's one.
there.
Yeah, there is a glare.
I wonder if that's
Switch it.
on the bottom.
Yeah,
Yeah.
the other one.
Okay. I don't know which
Should be the one on the left.
one. Okay.
Yeah, it's better.
Oh, yeah, it's definitely better. Okay. All right, so we have 1 over k factorial, and I'm going to take the t to the k and lump that in with the matrix entries, because we want to see what happens to each individual entry. So now our 1 to the k becomes t to the k. So now at least we really need the k. 0, and then we have 3t to the k. And then what we have is k 1/2, 3t to the k minus, and we had 1 before, right? Yep. But now that's just going to be t to the k. So now it's a bit easier to see what happens in the end. So, so if we take this power series individually, we're going to get e to the t up here, 0, e to the 3t, and then we have 1/2 e to the 3t minus e to the t. All right. So now that we have e to the at, we can now write down a general solution of the system that comes from this matrix. So matrix is 1, 1, 0, 3. So that's x1 prime is x1 plus x2. x2 prime is equal to 3x2. So that general solution is just e to the at times some arbitrary vector c that really is your values at t equals 0. So that's just going to be a matrix vector product. Bless you. Times the components of c. Okay. All right. So you can think of this as your alpha of t, as your solution curve for whatever initial condition you have. All right. So questions about this e to the at?
So how do you get the general solution to that?
Since this is a homogeneous system,
Right.
so it's just e to the at times your initial values.
Oh, so
It's always that.
right.
And if it was a non-homogeneous system, we would add on that integral term.
Right.
Yeah.
But how do you get like x1 prime equals x1?
Oh, from a matrix, because our matrix.
1, 1, and 0, 3, right?
Yeah.
Yeah.
You just read off the coefficients.
Right.
Any other questions? Okay. So now, section 4.4 of the book is god awful miserable section. This is so long. It's like 35 pages. All about, it's called the geometry of the integral curves. So for a general linear system, how do the integral curves behave? Mostly in 2 dimensions, because at least you can plot them. And that has a lot to do with what does e to the at look like. It depends on the eigenvalues and eigenvectors of A, so that you can get e to the at. So, so the thing is, in order to be able to discuss solutions and how they behave, you need to know about eigenvalues and eigenvectors. And to date, this has not actually exactly been a linear algebra course. It's been a DE course. So what I have to do to set up any of that, which I'll actually cover on hopefully on Monday, is I have to get all linear algebra into that and talk about eigenvalues and eigenvectors, because that's not supposed to be covered in 326, and no one ever does. And let's see, a couple of you have taken 426 or 526 and saw it there, right? Kinda. Yeah, that's terrible. Now 610, I bring it up because it's one of my favorite things, but only 2 of you have taken that. So, okay. So basically, actually, a lot of my notes for today are taken from the notes from one of my numerical analysis classes, just because it was already written up there. Okay. So, and once we know something about eigenvalues and eigenvectors, then we can talk about integral curves. Okay. Okay. Now, I mentioned that, well, actually, it's possible that some of you might not have even dealt with eigenvalues and eigenvectors and all. So I could not blame you if your first question is, what are they? Or maybe you knew it one time and have forgotten. Okay, so I'll just start with, so we're going to get very basic here. Okay, so A is a n by n matrix. So if you have a non-zero vector x, and I can't emphasize enough, it has to be non-zero. It's an eigenvector of A if we have this relationship, A times x, so this matrix vector multiplication is equal to lambda times x for some scalar value, so just a number, lambda, which is called the eigenvalue. So eigenvalues and eigenvectors come together in pairs. Okay. All right. Now, so to interpret this equation here, a times x equals lambda times x. So on the left side, because on both sides you have completely different operations being performed. Left side you have matrix vector multiplication. Kind of a tedious operation. You have to go across each row of A and then down a column X to get the first element, then across the second row of A, down X, to keep multiplying and adding as you go. You're taking n dot products of each row of A with X to get the result, which is a vector. On the other hand, on the right side, you have a very simple operation. So you just have scalar multiplication of the vector x by lambda. So eigenvectors are these special or magic vectors, if you will, that reduce this complicated operation to an extremely simple one. And that can be very helpful for performing certain manipulations involving A and understanding how A behaves. As you think of A as a linear transformation on your vector space, x is your input and ax is your output, so it's a linear function. How does this linear function behave? Does it shrink vectors, for instance, if the eigenvalues are small? Does it extend vectors if the eigenvalues are large? Does it reflect vectors, for instance, if lambda is negative? What kind of behavior do you get? So if we know something about the eigenvalues and eigenvectors, we get a much better understanding of A. Also, think about the matrix exponential. Matrix exponential is taking a function of a matrix. Taking a function of a matrix is much easier to understand if you think in terms of taking that function of the eigenvalues, because we're accustomed to taking functions of numbers, not of matrices. And so eigenvalues allow us to pass from one operation to the other. Okay. So here we have a definition, but now what can we do to actually find eigenvalues and eigenvectors? So ultimately, we'll need those in order to compute matrix exponentials and stuff. Okay. So, whoops. Yeah. Thanks for catching me there. So, starting from the definition, ax equals lambda x, so I'm just going to rearrange this, put everything on one side. So I have a minus lambda times the identity times x is is equal to the 0 vector. So I just put everything on one side and factor out an x on the right side. Now, here's where it's very important to use the fact that x is non-zero. So if you take a matrix and multiply it by a non-zero vector, and your result is 0, what that means is,
That has,
what?
wait, go ahead.
It's not invertible.
The determinant of that is 0.
Yes, as a result of it being not invertible. Because for an invertible matrix times any, when you have an invertible matrix, the only way to get 0 is to multiply it by the 0 vector, but x is non-zero. So it's not invertible, and what that means is the determinant of A minus lambda times the identity has to be 0. Okay, and this is the approach that we're going to use in the homework problems, which fortunately deal with really, really tiny matrices, to find eigenvalues. Because if you were to take a specific matrix A and write out the determinant of A minus lambda times identity, what you would get is, this is called it's actually a polynomial function of lambda. So it's the characteristic polynomial of A. So let's call it P of lambda, just to call it something. And because A is an n by n matrix, it has degree n. So you have a polynomial of degree n, therefore you have n roots. So what you get is an n by n matrix and n eigenvalues altogether. However, because you have these are polynomial roots, so you can expect all the kind of behavior that you might get from polynomial roots, which means they might repeat. So like you might have a double root, so you could have a double eigenvalue or eigenvalue of any multiplicity. Or it might be complex. Now we're going to assume that A itself is a real matrix, but you can still get complex eigenvalues. But if you have a real matrix that has complex eigenvalues, what do we know about them? How do the complex eigenvalues of a real matrix relate to one another? Or
Conjugates?
yeah, they have to be complex conjugates. So they have to occur in complex conjugate pairs. So that's something that's going to help us later on when we study solutions. Okay. Okay. All right, so I'm going to do a quick example here so you can see how this works, for instance, for a 2 by 2 matrix. So let A be a general 2 by 2 matrix, A, B, C, D. So now we look at the determinant of A minus lambda times the identity. So we're just using a formula for a determinant of a 2 by 2 matrix. So that's going to be A minus lambda times B minus lambda minus BC. So this is the characteristic polynomial, which I previously referred to as P of lambda. But let's go ahead and multiply this out and you get something interesting. Because what you get is lambda squared minus A plus D lambda. And you get plus AD minus BC. Okay. Now, AD minus BC, what is that? That is the determinant. So that's the determinant of A, and for a matrix in general, the determinant of the matrix is actually the product of all the eigenvalues. So even if these eigenvalues turn out to be complex, the determinant is going to be real. A plus D, what is that? What property of a matrix does that represent?
The diagonal.
Well, keep going. Yeah, it's the sum of the diagonal entries. But what do we call that?
Trace.
Yes, it is the trace of A. And the trace for a general matrix is the sum of all the eigenvalues. So those are some good to know things. And actually something about quadratics that you may or may not know. That when you have any quadratic, AX, assuming the leading coefficient is 1. So x squared plus bx plus c. C is the product of the roots. Minus b is the sum of the roots. So that could be a way to, you can figure it out basically when you're dealing with factoring, which I imagine comes up in college algebra. Well, yeah, you guys in Math 500 taught about that. Well, that's right. The rest of you four are going to be taking Math 500 next semester. About getting ready to teach here. So I had to prepare a college algebra topic and teach
We
it.
know that breaks up, right? It's like the sum of the external.
Yeah.
You can factor it out if you can express that as a sum in a way that it could be the product of that.
Exactly. Yeah. So really, it ties into all this. So this is just another way of looking at that same thing. Of course, when you're trying to factor something by hand, you're hoping it works out nicely. But yeah, it works in general. Okay. So now you can go ahead and take the roots of this. So the eigenvalues, which I'll call lambda 1 and lambda 2, are just going to be roots you get by a quadratic formula. So it's going to be a plus b over 2. So 1/2 a trace plus or minus square root of the trace squared. Okay. Well,
Minus 4 times the determinant, right?
why did I write it this way? It's strange. Oh, okay. Yeah, so another way of writing it, just by simplifying, you write it as a minus d squared plus 4bc all over 2. But that's the same thing as square root of the trace squared minus 4 times the determinant. Okay. So of course that could turn out to be complex, but at least you're going to get complex conjugate pairs. Okay. Now, let's see how I'm doing on time here, because I may not necessarily talk about every little thing that's in my notes, however tempting that might be.
AC, right?
What?
The rule is 4AC, so it becomes 4AD minus B.
Well, the thing is, the A, B, and C here are not AX squared plus BX plus C. They're A, B, C, D from this matrix.
Oh, so they cancel out.
Yeah.
4 AD cancel.
Right. Yeah, that's how
Minus 2 AD.
that's how the plus here becomes a minus in here. So,
Oh,
actually, in fact, from this formula, you can easily see why, if A is a symmetric matrix, which means B equals C, we'd have a sum of squares here. Therefore, guaranteed to be real. The eigenvalues of a symmetric matrix are always real. Okay. Okay. Now, all right. So for purposes of computing e to the at, we need to know about certain decompositions of a matrix that relate to its eigenvalues and eigenvectors. Okay. So all right. So first, a very important definition. We say the two matrices A and B, and we'll stick with real matrices here. but it applies just as well to complex matrices. We say that A and B are similar matrices if we're related this way. If B is equal to X inverse AX for some invertible matrix X. Okay. And this basically transformation of A to get B, where you're multiplying the left by a matrix, multiplying the right by that same matrix's inverse. I almost committed a cardinal sin of this total fingernails on chalkboard when someone uses, when they say, they mean matrix, but they say matricy in the singular, so don't do that. Okay, this is called a similarity transformation. Now, the important thing about similarity transformations is they're similar matrices for our purposes, is that A and B have the same eigenvalues. Okay. So in fact, it's this key idea that is an essential ingredient in algorithms, numerical algorithms, for computing eigenvalues. That starting with your original given matrix A, you come up with some sort of similarity transformation of A into another matrix B, for which it's much easier to get the eigenvalues. All right. Now, A, in our case, can be anything. What kind of matrix do we want it to be similar to in order to be able to just read off the eigenvalues? Precision erasing.
That's so great. Good one.
Okay, so now that I've assured myself that I've not lost anything, it's a good thing I was paying attention to that. I just happened to hit the mouse pad at the wrong time. Okay. Okay, so when is it easy to get the eigenvalues? Is there a situation where you can just read them off a matrix? Yes, and so more generally that if A is
Forget everything.
A is triangular, it doesn't matter.
Upper and lower.
Yeah. So upper, lower, or if it's both upper and lower, so diagonal is a nice special case of this. Then the eigenvalues are equal to the diagonal entries. Okay. So one thing we're particularly interested in is the following. If A can be written as x dx inverse So D is a diagonal matrix. Then A is diagonalizable. Okay, so that's what we like to have, this diagonalizability. Now, one consequence of this, though, because so the so the eigenvalues in this case are equal to the diagonal entries of D. So dii for I equals 1 to n. So we can just read them off the diagonal of D. Also, the eigenvectors are the columns of X. So then we know everything about the eigensystem of A in the case where it's diagonalizable. It's very convenient. Okay. Actually, we don't really need this here, but it's a side comment. So this is the columns of X are the eigenvectors of A. The rows of X inverse are the eigenvectors of A transpose. A and A transpose have the same eigenvalues. Right. But X is invertible. So if the eigenvectors are the columns of X, what that means is the eigenvectors are linearly independent. One of my least favorite terms to write out in full. And because you have n of them, and the dimension of your space, your vector space is n, they form a basis for not Rn. I need to say Cn, and the reason for that is even if A is real, the eigenvectors might be complex because the eigenvalues might be complex. So if you have n linearly dependent vectors in a space of dimension n, they describe a whole space, therefore they form a basis. Okay. All right. Now, when are eigenvectors linearly dependent in general? So there's one nice result about that. I actually take the time to, I prove a simple case in the notes. So I won't go through the whole proof here, but what can be shown is if you have a set of eigenvectors so let's suppose we have k eigenvectors and k eigenvalues that go with them. And all of the eigenvalues are distinct. So if all the eigenvalues are distinct, then it can be proven using a simple inductive argument that all the eigenvectors that go with them are guaranteed to be linearly independent. And the thing is, so the notes I have why this has to be true in the case of two eigenvectors, because if you have two eigenvectors for two different eigenvalues, and they're multiples of each other, you multiply it by A, you can get it times either eigenvalue, which are different, which is a contradiction. You can't have A times a vector be equal to two different things. So they have to be independent. Okay, actually, one thing I accidentally glossed over because eigenvectors are not unique. Any multiple of an eigenvector is also an eigenvector. So when I talk about eigenvectors, I'm really talking about an eigenvector and all scalar multiples of it. So you can think of it as an eigenspace. In fact, it's often called that. So you can think of it as a one-dimensional vector space. So often eigenvectors are normalized, like make them a unit vector, for instance, to try to give some sort of uniqueness. So when we talk about different eigenvectors for different eigenvalues, we're talking about different eigenspaces, so eigenvectors that are linearly independent of one another. Okay, so the bottom line here is different eigenvalues lead to linearly independent eigenvectors. Okay, so what that means is if your matrix A has n distinct eigenvalues, you have n linearly independent eigenvectors, so A is definitely diagonalizable in this case. Okay. Now, so what if A, this is where things get dicey. What if A has repeated eigenvalues? In that case, we don't know. This could go either way. So A, it may or may not be diagonalizable. And non-diagonalizable matrices are a real pain to deal with. In fact, what I'm about to get into to discuss this further is only really useful for working things out by hand, dealing with exact arithmetic. Because anything I'm about to show here is actually completely useless in a numerical setting. Because suppose you go ahead and compute eigenvalues numerically, and you have, for instance, two eigenvalues that you believe are equal to each other. Like say they're both equal to 2. But maybe one of them is exactly 2, and the other is like 2.0001. Well, are they really meant to be distinct eigenvalues that happen to be close together, in which case the matrix is definitely diagonalizable? Or are they meant to be the same eigenvalue, and one is just a little bit off? And then the matrix, in that case, might not be diagonalizable. So in a numerical setting, you're out of luck. But for simple problems, small matrices where you can work things out by hand, all this is very important because it affects what kind of solutions you get to your system of DEs. Okay, for example, when you took your DE class and you're solving second-order equations, you have your characteristic equation, you get your two roots. So for instance, if they're real, you have your exponentials. If they're complex, you have your sines and your cosines. What happened if you have two roots and they happen to be equal? Like, if you had two roots and they're both equal to 4, so you'd have e to the 4t, and what was your other solution? Because you couldn't have another e to the 4t.
You square the.
No.
Wait,
You mean
When you have
minimum
repeated
complex,
roots?
or-
No, it's still real.
when you have repeated roots,
Yeah, repeated roots.
you don't, I thought you increased the power of the,
It's like a coincident.
Power of what, though?
you multiply it by the root and like you multiply, like if the roots are, you say r times either whatever, but you say r squared the next time and r cubed, right? I just remember writing it like that.
Not quite.
No, never mind, I quit.
Okay. You need a factor of t. So you have like e to the 4t and t e to the 4t.
Oh,
And if the
so
root,
that's where I was thinking the r. I used to write it as r.
okay, and
So
if
that's why
and if the
it's
root
r.
repeated
So
again,
r is
you'd
r
have even
times
more
t.
higher powers of t. Like if it repeated 3 times, you'd have
T.
e to the 4t, t e to the 4t, t squared e to the 4t.
That's what I was talking about. I
Okay,
just
yeah, I
phrased
wondered
R.
about that. Okay.
I wrote them as R, not T.
Okay, you're almost there.
You don't have T or R up there. You don't have a certain letter up there for it.
Yeah, but I'm talking about.
Well, whatever.
Okay, so what you're about to get an idea of where it all comes from, because it actually comes from non-diagonalizable matrices. Okay. Okay. Yeah. So when eigenvalues are distinct, that's an easy case. We'd like to have that happen, and actually I think that does happen in pretty much any of the homework problems I give you. But it's important to know about the non-diagonalizable case too, because that totally affects the structure of your solution. Okay. All right. So I need to introduce some terminology to be able to talk about this. Okay. So any eigenvalue. Now, eigenvalues may repeat because they're roots of a polynomial. So there's a certain multiplicity there. But eigenvalues actually have two notions of multiplicity. So the first one is called algebraic multiplicity. Okay, and I'll call that, okay, so I'll call the eigenvalue lambda I. So we have always eigenvalues lambda 1, lambda 2, etc. So algebraic multiplicity, I'll call that m sub I. Now, this is a multiplicity that you're more familiar with. So this is just the number of times that lambda I is a root of your characteristic polynomial. So that's the algebraic multiplicity. So if you have like lambda minus lambda I 5 times in your factorization of p of lambda, the algebraic multiplicity is 5. Okay. The geometric multiplicity called GI is the number of linearly independent eigenvectors that you can associate with this eigenvalue. So you can have a root repeat, have an eigenvalue repeat, a zillion times as your characteristic polynomial, but there might still only be one linearly independent eigenvector. So what we know about the geometric multiplicity is that it's always at least one, because you have to have n eigenvector, and it's always less than or equal to the algebraic multiplicity. All right. Now, if the geometric multiplicity equals the algebraic for all eigenvalues that you have, and that's a diagonalizable case. You actually have a full set of eigenvectors. On the other hand, if the geometric multiplicity is strictly less than the algebraic, then that eigenvalue is called defective. So these are the repeat eigenvalues that are a real pain to work with. Okay. Oh, and one other term I'll throw out there that's fairly common. If both the old multiplicities are equal to 1, then we say that
Simple, right?
yeah, it's a simple eigenvalue, just like a number that is a single root. So the number is not a double root. Well, a function is called a simple root. Okay. All right. Wow, all this time I only got through 2 pages of notes. Sheesh. Okay. Ooh. Okay, so some of this is going to spill over into Monday. Oh well. So to account for all these possibilities, where matrix may or may not be diagonalizable, you may have defective eigenvalues, we have what's called the Jordan canonical form. Okay. Let's see where I'm going to put this. So every matrix A, square matrix, has a Jordan canonical form. Okay. So here's a decomposition, xj, x inverse. So J is this Jordan canonical form, often abbreviated as JCF. So it's the matrix J that we're really interested in. And J has a particularly nice structure. I might as well go work my way around all the stuff. So it has a block diagonal structure. So it has blocks J1, J2 up to JP. Okay, where P happens to be the number of linearly independent eigenvectors. So if a matrix is diagonalizable, you have n of these blocks, but each block is 1 by 1. It's a number, so you have a diagonal matrix. Okay. Now, what about the individual blocks themselves? So each of these blocks, which is called a Jordan block, has this form. You have an eigenvalue along the diagonal, and then you have ones right above it on the super diagonal, and then 0 everywhere else. So it's an upper bidiagonal matrix. Okay. Now, the number of blocks that have a certain eigenvalue on a diagonal is equal to the geometric multiplicity. Because each block is associated with one linearly independent eigenvector. So you can have multiple blocks that have the same eigenvalue on them. And I'll give an example of that in a little bit. On the other hand, the sum of the sizes of the blocks that have lambda I on the diagonal is equal to the algebraic multiplicity. So if an eigenvalue has any block like this, or is 2 by 2 or larger, that has any ones up above, it's defective. So we don't actually like to have these kind of blocks. We like blocks that are just numbers, because that's a diagonalizable case. Okay. So an example, let's suppose a matrix has this Jordan form. So I have a 3 by 3 Jordan block for the eigenvalue 2. And then I have a 2 by 2 Jordan block with the eigenvalue 3. And then I have a 1 by 1 Jordan block, again with the eigenvalue 2. So here are my two distinct eigenvalues. I have an eigenvalue that's 2, and another eigenvalue that's equal to 3. So for both these eigenvalues, I can talk about their multiplicities. So I can say that for 2, the algebraic multiplicity is 4, because I have a 3 by 3 block here and a 1 by 1 here, added together to get the algebraic multiplicity. But how many blocks do I have associated with 2? 2 of them. That's the geometric multiplicity. So I only have 2 linearly independent eigenvectors associated with the eigenvalue 2. On the other hand, for the eigenvalue 3, I have an algebraic multiplicity of 2, because I have one 2 by 2 block. But because I only have one block, the geometric multiplicity of 3 is 1. So I have a 6 by 6 matrix here, but I only have 3 linearly independent eigenvectors. So this is totally not diagonalizable. Okay. So in fact, certain situations where you can tell if a matrix is not diagonalizable just by looking. So I have a matrix like this that has same number on the diagonal, and it's triangular, but I have a non-zero number b up above. That is also not diagonalizable. So this can be a pain, like numerically, if element b is particularly small. How do you know it's not really meant to be 0? So that one little change makes causes the matrix to either be diagonalizable versus not diagonalizable. Okay, and that's why repeated or nearly or closely clustered eigenvalues are a pain for computationally, but doing things by hand, we don't have to worry about it. Okay, so if you only have, in this case, a 6 by 6 matrix, but you only have 3 linearly independent eigenvectors, what else do you have? You have what are called generalized eigenvectors. Okay, do I have enough time to talk about that?
It's 442. 443. Okay, just changed.
Okay. I'll just talk about this, it's not much, and then I'll stop. Unfortunately, it doesn't get me through everything in these notes, but honestly, I don't care about that because there's
You
one
said
thing.
you didn't like this. There was one section you didn't care if you didn't get through. I have a feeling it wasn't this one though. You like this stuff.
This stuff, yeah. Because I budgeted spending 3 whole lectures
On
on
this?
4.4, just because how many pages it was, and it might not really turn out that way anyway. So, and that's perfectly fine with me. I'm also weighing what to do about there's 2 classes that are going to be canceled coming up, and I haven't decided about the month that are both Wednesday classes, and I haven't decided about the Monday in between yet.
So you can assign like 2, 3 columns from this guy.
If you're gonna you mean if you're gonna cancel it or just
Right.
for the 2 of us that are gonna be here?
Oh no, for that class I'm canceling.
Oh.
It's the one right before fall break. Huh?
There's one right after fall break for Monday
Oh.
when all you Siamers are still here. Although some of you will be preparing to leave early in the morning. Who's doing the early shift? Well, not you.
Teresa.
Teresa's probably doing the early.
Yeah,
Are you running early?
I'm going with Teresa.
Okay, yeah.
She's even at
Okay, so
6.
you're the only one who's in this group.
Yeah, I got volunteered to do that one. How that happened.
Yeah, you can
It
dump
didn't
with me
matter.
too.
I was just like, oh, we're leaving at 6 a.m. It's
We have a
lovely.
faulty car.
Yes, a faulty car.
The fault lead.
Yeah.
I don't know.
No, not even the fault lead, the
Are you
fault
driving?
lead.
I'm driving.
Falsely,
I'm
or
driving.
you're
Yeah, I was thinking
Well,
about leaving
Yeah,
later.
I
driving.
like it.
I've had this
I can drive, but I don't know license.
Assuming it's not actually faulty. Have I used it one more time already? 1 minute. Okay. Still trying to finish. Okay. Alright, so what happens is, alright, so I have AXJ is equal to XJ times a Jordan block. Wait, these are I's. Okay. Alright, so this is one of these Jordan blocks like what I have over there. And this set of vectors, I'll call x1, x2, up to xk. So this Jordan block is k by k.
Those little little X's are big.
These are little x's.
Little X's.
Okay. So the Jordan block has an eigenvalue, lambda I, all repeated all the way down the diagonal, and once down here. So if you write out this matrix equation here, column by column, then okay, still get out of here plenty of time to enjoy real analysis. So you get AX1 is lambda x1. So that is an eigenvector, plain old eigenvector. That's the only linearly independent eigenvector you get. Then you get AX2 is lambda x2, and then because of a 1 up above, you add on a term x1. And then similarly AX3 is lambda x3 plus x2, and so on, all the way down to AXK, the last one, is lambda xk, these are lambda i's, okay, plus the previous one, xk minus 1. So now what you do is you rearrange these. So x2 all the way up to xk are called generalized eigenvectors. Okay. So the way that so what happens is A minus lambda identity xj for each of these generalized eigenvectors raised to the j power. Sorry, I need to rewrite this because I didn't allow myself enough room. A minus lambda I identity to the j power times xj is 0. Because if j is 1, this would just be a plain old eigenvector, but I need to raise this to a higher power to make that happen. So if I take this and rearrange this for all of these guys, I have A minus lambda I identity xj equals xj minus 1. So this is how, this creates a chain of generalized eigenvectors. So what I can do, and this is where I will stop, is use this relationship that describes a chain of generalized eigenvectors to show you how to get all of them on a specific example. So first thing you do is you solve the equation A minus lambda identity times x1 is equal to 0. So that is, first you get your regular eigenvector. Okay, and then you solve this chain of system of equations. A minus lambda I identity times xj is equal to xj minus 1, for j equal 2, 3, etc. And these are your generalized eigenvectors. Okay. Now, the question is, when do you stop? I actually looked this up on various sources online. They have procedures for determining when to stop, and they are so unbelievably impractical, it's kind of disgraceful, actually. I can give you a simple criterion for when to stop. You keep trying to solve the system equations until the system is inconsistent. Because you're solving a system, you're doing a Gaussian elimination on both sides. To try to figure out what your solution is. At some point you get to a situation where you have a contradiction. Something non-zero equals 0, and you're done for. So that's actually what happens in this case. And if I had the time, I could actually show you why that happens. Now, if you're dealing with a small matrix, you probably know when to stop anyway, just from the size of a matrix. But like a 2x2 case, if you have a double eigenvalue, you get an eigenvector, you have one generalized eigenvector, and that's it. So once you fill the whole space, you're done anyway. But that's what you do. So once you have that, the result is A is equal to xj x inverse, where the matrix X consists of all linearly independent eigenvectors and generalized eigenvectors. And once you have the Jordan form, or ideally, J would actually be a diagonal matrix, needs to be eigenvector. So it doesn't matter. Either way, once you have that, you can compute e to the at, which is x e to the jt x inverse. So taking exponential matrix, you just only have to apply it to a Jordan form, which is a whole lot easier. And I will talk more about that on Monday. Okay. How far did I go over? Oh my God, 6 minutes. Sorry.
So, how about that example there, like the MI and the GI? So, how do we know how many generalized eigenvectors do we have?
Well, the thing is, first, when you get your eigenvectors, you might have more than one eigenvector. That comes from a rank of your system, A minus lambda identity. So you just get all the eigenvectors you have. Each eigenvector starts its own chain.
Okay.
So,
Yes, but like, are we gonna have only one, or are we gonna have three? Like, how can we tell?
from this example,
Yeah,
okay, you get two eigenvectors,
right.
and then you try to solve systems with your eigenvectors as the right-hand side. And this one, you won't be able to solve at all. It'll be inconsistent immediately. So this produces no generalized eigenvectors.
This guy. Right.
Yeah. So you get the two eigenvectors, and that's why you get the geometric multiplicity of 2.
Right.
And then this one does not produce a chain.
No.
This one produces a chain that has two generalized eigenvectors that go with it until you can't solve anymore.
So, well, this guy has two.
Yeah. Two generalized eigenvectors added to the regular eigenvectors gives you an algebraic multiplicity of 4.
Two general and two real.
Yeah, two regular.
And then this gives you 0.
Yeah, there's no chain. Here you get one regular eigenvector that gives you this,
Right.
and you can get one
One
generalized
chain.
eigenvector, one chain. Yeah.
So you get 2.
And then once you have a total of 6 vectors of any kind, you know you're done because the total dimension of your space.
Space is
The
6
six.
because, yeah.
Yeah. Okay. I hope whoever's listening to this benefited by hearing that.